All right, so we are going to start a new unit today. I'm not sure when we're going to do the lab yet, mainly because I am still struggling with something. And I don't know if it's viral or what it is. And I want to do the lab on a day where I've actually got some energy to help you with the lab. So we're going to do notes today. In terms of the assessment of this unit, it's going to be a little different. We are going to be doing this not through tests primarily, but rather by projects. So there's going to be 3 different projects. This unit is made up of several different concepts that are this word here on the board that you probably can't read. It says illustrative examples. And illustrative examples means that they are really good examples of the concept of homeostasis. And as such, they are ones that might be tested on, or you might be asked to give an example of homeostasis, and these would be good examples to use on an AP test. So that's why we're going over them. So there will be 3 projects. There will also maybe be an essay, short answer essay type of test. I have not decided on that one yet. We'll see what happens. I think now if I go to, let's see, I think I can just do this by, I think if I open up a new window, you're not going to see it in Screencastify. Yeah, no. So let me see if I can do this the old-fashioned way. Yes, we're going to start with chapter 40 first. I'm going to do this a little bit out of order. That's the class drive. I don't want the class drive. Or do I want the class drive? Yeah, no, I don't. Why does it keep opening up windows? I want a new window open. All right. There it is. Oh, Jesus. Oh, my God. It refuses to open it up in this window, and I need it in this window or a Screencastify won't record it. All right. Yeah, so we are going to do the chapters a little bit out of order. Everybody has a little slightly different way of doing these chapters. Obviously, the authors of this textbook had a different way of doing that. But fairly early on, we start talking about how cells interact with other cells and how they function differently under different circumstances. And then that really brings up homeostasis. So we're going to start with chapter 40 today, and then we'll come back later in this unit to more of the order that we've been through. But everything's organized by units rather than necessarily by chapters. So just because a chapter is not sequential doesn't mean it's out of place. So chapter 40 talks a lot about body plans and systems, and we're not too worried about that. There's all sorts of organ systems in the human body. Unfortunately, we don't really talk about these like we used to. We used to have a whole unit, actually 3 units on different systems in our body, which was awesome. I really liked it. But we're not going to really talk about that anymore. Unfortunately, they've gone away from that. There was a unit on nervous system. So people who are in psychology probably know a little bit about that already. There was also one on coordination and movement, in other words, muscles. So we talk about how muscles would move, how that would happen. And also about endocrine system. Endocrine system, we are going to talk about. We're going to do that in a little bit. We're not going to do that today. We're going to do it a little bit later on. Nervous system, these three units that I just mentioned, nervous system, muscles, and control, are all important because they are all involved in that homeostasis. So nervous system is going to be responsible for transmitting information to and from kind of the control center, that being the brain and the spinal cord. Nerves send messages that are very, very quick, and so we can get a message to different parts of the body very quickly. And that system, nervous system, is going to work very closely with this other system that I talked about in that last slide, which was the hormones, or the endocrine system with its hormones. Endocrine system and nervous system work very close together, but they're kind of opposites in terms of their extremeness. Nervous system works very, very quickly. Endocrine system traditionally works kind of slow in terms of our body. It's kind of on the other end of that spectrum. But it is all part of communication with our body and telling our body, hey, this is going on. We need to deal with this. So this picture shows you on the left-hand side, you have the endocrine system. So here we have a cell that acts as a stimulus, and it sends a message, and its message is by way of these things called hormones. And in the endocrine system, those hormones travel through the bloodstream, and they have a very widespread effect on the body. Signaling by the nervous system is going to be a little bit different. There are nerve cells that they're funky shaped. They're very funky shaped. They're called neurons. And they will send a message, could send a message to another part of the body, but they could just send a message to another neuron in the brain. So it could just be you just sitting there thinking, and your neurons, your nerve cells, are communicating with each other that way. So it's usually a pretty specific. So a specific location here, and in the hormone system, the signal is going to travel pretty much everywhere. Second part of that is on the slide below. Once it gets to the target, once the hormones get to the target, they are going to leave the bloodstream, and they're going to cause a response in some type of cells. And the same thing's going to happen in the neurons. But again, it's going to be more localized in the nerve cells than in the endocrine system. Come on. Okay, so when we talk about communication, we need to talk about the fact that an organism's environment is usually not constant. It's usually fluctuating. And because of that, the body has to react to conditions that are going on. Last Tuesday, right? Today's Tuesday. Last Tuesday, it was 80 degrees, right? And what is it now? It's snowing. Okay, so a week later, it's snowing. So we as human beings, rabbits as rabbits, and snakes as snakes, they all have to figure out a way to deal with those fluctuating conditions, right? Those environmental conditions are constantly moving. And so that has to be maintained. And so the systems that are going to be responsible for maintaining those internal values so that you don't freeze to death, for example, are going to be our nervous system. And oops, I didn't mean to cross that out. I mean to cross underneath it. Nervous system and the endocrine system. Okay. Before we go too much farther, though, we need to talk about this idea of what a regulator is and what a conformer is. A regulator is an organism that will try and change its internal conditions to deal with what's going on in the environment. You can contrast that with a conformer. And conformers tend to just kind of live and let live. And if it's colder outside, then they're going to be colder outside. Whereas a regulator is going to shiver to try and bring that body temperature up. A conformer is going to say, yeah, I can go down. I can be a little bit colder than I was before. I can go down a few degrees with my body temperature. So conformers just try to deal with and adapt to, I shouldn't say adapt to because that's not really correct, just try to conform to the environmental conditions. Okay. So here we have, in the next slide, we have an example of two different adaptations. The one on top here, what is that? What is that little guy? He looks like an otter, doesn't he? An otter. An otter is a mammal, and it is going to regulate its temperature, so it's going to stay the same. And that's the little guy on top here showing you. Doesn't matter if it's really cold outside, if it's close to freezing, or if it's 40 degrees, it's going to keep the same internal body temperature. Anybody fish? This looks like it looks like a bass. I think it's a bass. Bass are conformers. These guys are just going to fluctuate. Their body temperature is going to fluctuate with the temperature of the water in this case. And so we see that it changes dramatically over a range of 40 degrees Celsius. And those are the conformers. And so these guys, bass, yeah, I guess. Conformers tend to be able to conform to a larger temperature range than regulators can. Regulators, it's usually a smaller range that they can deal with before things really go wrong for the body of that organism. This is where I'm going to talk about my turtle story, right? I know you all wanted to hear my turtle story, right? It is sad. Well, I kind of gave it away at this point. Can I draw a turtle? That's his head. Turtles do have little tails. Did you know that? That could be so many things. Yeah, it could be a dog too. Crab. Oh, it could be a crab. You're right. All right, this is a fail. Anyway, so when I was a kid, we didn't have this thing called the internet. And let me back up even farther before we get to that. So when I was a kid, I used to go to a lake and I would catch turtles. And one time I took a turtle home with me. It was going to be my pet for the winter. And I had it outside in this big tub of water. And as it got colder, the turtle moved less and less. Okay, I'm like 8. Okay, cut me some slack here. I'm about 8. And I'm like the smart one, right? I'm like, no internet, but we have a library. So I went to the library and I looked up books on turtles. And turns out turtles are not regulators. They're conformers. So they will conform to the temperature around them to a certain extent. And in the winter months, they burrow down in the bed of the lake, in the muck, and they hibernate down there during the winter. Well, I lived on a farm in Iowa where there was no lake. So I was like, what am I going to do with this guy? I had a brilliant idea. I'll dig a hole for him. because he can't burrow, right? So because he doesn't have mud, so I can burrow for him. So I dug a hole for him and I put him in the hole and I covered him back up. At this point, he was almost not moving at all, right? Because he's gonna go hibernating. I'd figured out he's gonna go hibernating, right? Yeah. So you know where the story's going. You know what a freeze line is? Frost freeze line. So far down in the earth, if you get below a certain point, the earth, because of the warm from the core coming back up, the earth does not freeze. But you have to get below that frost freeze line. And I dug a hole that was like 2 feet deep. Yeah. So Tiny was his name. Tiny was kind of frozen when I picked him back out of the hole. Because he was conformer. He hibernates, but yeah. So I froze the turtle. I was 8.
Did you understand?
I think I went back to the library and then was like, oh yeah, there's that. Oh, oops. Sorry, Tiny.
Did you try it again?
I did not try it again. Once was enough.
Probably would have been more successful.
Yeah, I would hope I'd have been more successful. I don't know if I could get below the freeze line though, because that would have been pretty deep. I think maybe 6 feet. Yeah, it gets pretty cold there.
It's like they freeze.
Right? Yeah. So the water would also moderate the temperature, right? Because yeah, very good. Nice connection. I like that. All right. So yeah, that's my digression for the day. Homeostasis is the word I've been kind of bantering around, but I haven't explained what it is. Tiny was not an organism that could maintain homeostasis. He was a conformer. But regulators are ones that can control their internal temperature. And even when it gets colder or gets warmer, they will maintain that internal that internal pH, that internal glucose level. All of these are things that in humans we're able to regulate. And we're going to talk about all of these systems. The way those systems are regulated is through a combination of both the nervous system and the endocrine system. Okay, so the concept of homeostasis is fairly straightforward. Think about a thermostat in your house. It keeps the heat, or I should say that, it keeps temperature at a constant value. If you have your house set at 68 degrees, for example. If it gets hotter outside, your furnace is going to turn off. And if you have AC, I don't, but if you have AC, the AC will kick in. Okay? If it gets below that, let's say it gets down to 65, the AC is going to turn off and the heat will kick in. Okay, that's homeostasis. You've got what they call a set point. And when the value differs, when the actual value differs from what the set point recommends, the system, in this case our bodies, will react to that. So that if you get below that set point or above that set point, you have some type of stimulus, an increase in heat or a decrease in heat. And then there's going to be a response. And that response is going to trigger either, in our case, it's going to trigger either the air conditioner to turn on or the heat to turn on. And it's going to bring it back to that set point. So here I've got my room temp at 20 degrees. What is that? 20 degrees Celsius. Is that 75? No, that's too high. 69. Hey Siri, how many degrees Fahrenheit is 20 degrees Celsius?
20 degrees Celsius is 68 degrees Fahrenheit.
All right, so it's 68. Right, that's 68. So we have a set point, and that set point is 20 degrees. But if the room temperature starts to decrease, let's say all of a sudden it gets down to 65, your heat's going to turn on. Some of you might have forced air, some of you might have electric, some of you might have radiator heat. But whatever it is, it's going to turn on, and it's going to bring the temperature back up to our 68 degrees Fahrenheit. Okay. Now we have a day like last Tuesday where it's 80. And now what's going to happen is, in this case, they're not showing the AC. They're just going to turn off that heater. Okay, this guy's going to turn off. Temperature will go back to that set point. Yeah, Mary. That's not a dumb question. I'm not sure the answer to it. I mean, I know our enzymes work at that temperature, but then the question is, why did our enzymes adapt to that temperature and not something that was closer to? Yeah. Oh, yeah. Yeah. Very good point. I got to think about that one a little more. I'm not sure the answer to that. Yeah. It's a good question. So in this, we have those set points. And then we also have what we call feedback. Feedback is to bring that value, that temperature in this case, back to the normal range. And normally in homeostasis, we're dealing with negative feedback. We're trying to bring it back. Okay, we're trying to bring it back to 68 degrees. It is possible to also have a different type of feedback where you actually continue to amplify the stimulus and drive it farther and farther away from the set point, and that's called positive feedback. That doesn't happen too often in our bodies. A potential example of that would be a fever, right? Your body temperature is set at that 98.6, but when you're sick, your body raises the temperature so that you are driving it away from the set point. Okay? Because until you get rid of that infection, you want to keep that temperature elevated. So that would be an example of positive. And I'll talk a little bit more about positive feedback, I think, in the future. But let me, since we're talking about it right now, let's talk about positive feedback. So fever would be one. Another one is childbirth. What happens to the rate of contractions as you go into labor? They increase, right? They become more and more frequent. Okay, so they're driving it away instead of decreasing their contractions, because if you decrease the contractions, the baby wouldn't come out. So you want to increase those contractions, and they get more and more frequent. So it's positive feedback. The other one would be breastfeeding. When the infant starts to suckle, that triggers a response that causes milk to be released from the mammary gland. Well, you want that to keep happening. You don't want the child to take one drink and then, oh, sorry, that's it. It's like, you're done. Right? As long as that stimulus, the suckling of the infant happens, the milk would continue to be released. Okay, so it's a positive feedback. All right, questions on that? All right. The other kind of cool thing about homeostasis is most of these things are in there's a set point, but there's a range. It's not like just, for example, your body temperature is not just 98.6. You're warmer, I think at night. Let me check that one. than in the morning. But don't quote me on that. I'm going to bring up another picture in a second, because they fluctuate around these things called circadian rhythms. Our body knows approximately what time of day it is. It knows what time of day it is, even if we're in the dark. They have done studies where they've kept people in the dark, and they tend to still run around a 24-hour clock. Okay, so even if it's dark 24/7, the body still knows it's about midday, for example, or it's midnight, which is kind of cool. Okay, yeah. So body temperature does tend to increase throughout the day. So you ever notice when you get a fever, it's worse at night? Yeah, because your body temperature increases and peaks around 6-7 o'clock at night anyway. So if it's already going to be the hottest that it's going to be all day, and then you got a fever on top of it, it's going to be the hottest during that part of the day. And then at night, it tends to fall off, and then it tends to raise back up again in the morning from 6 to 10 a.m. Okay, and that raising of the temperature is actually what wakes you up in the morning. That says to you, "Oh yeah, it's time for me to get out of bed." That's the trigger. And then along with that, this thing called melatonin. Anyone heard of that? Melatonin can change your sleep patterns. And so you take melatonin. Some people don't have enough of it, and they'll take melatonin before they go to bed, right? Because melatonin levels are low around 10, and then they start to crescendo overnight to keep you asleep. So people will take a melatonin to help them sleep at night. And you can also do that as a way to relieve jet lag. So you can take that melatonin, it's for your body. You go somewhere and your body thinks it's 6 o'clock in the morning. You can take that melatonin and gradually your body will, or more quickly, I should say, adapt to the fact that no, 6 a.m. is actually 10 at night. So figure that out. We talked about that. Sorry, I'm going the wrong way. Okay, so the rest of these for chapter 40 are going to be examples of homeostasis. One of those is thermal regulation. Thermal meaning temperature. So you're regulating temperature. And like we talked about before, we have those conformers and we have those regulators. We can put those into different words, and we can call those, we could also call those endothermic. Endothermic is going to be a regulator. Those are the ones that maintain their body temperature by heat. It's the heat that, as we know from the last unit, lots of the energy that we eat or the food that we eat gets lost as heat energy, and we use that to keep ourselves warm. Birds and mammals are all endotherms. And then we have, on the other hand, we have the conformers. These are conformers usually can adapt to a wider range of temperature values. They get their heat from external sources. So you see poor Tiny, on a rock sunning himself when it's a cool day. You go out on the rock to warm yourself up. Snakes do it as well. Reptiles in general, amphibians, fish. But if it's a really cool day, if it's a really hot day, if you're a fish, you're going to go to the bottom of the lake where it's colder. You're trying to get away from that heat. Okay, if you're a snake, you're going to go into a little crevice and hide out. So ecto means external. You're using external energy source to heat and cool yourself. And endo means that you're regulating it, and you're using, again, you're going to use homeostasis if you're an endotherm. You will not use homeostasis if you're an ectotherm. Endotherms maintain stable body temperature even in large fluctuations in environmental temperature. Endothermy is more energetically expensive than ectotherms. You're going to use a lot more energy to keep yourself warm than a little critter who just crawls out into the sun to stay warm. In general, ectotherms can tolerate a greater variation in internal body temperature. And a couple examples there. I got the walrus. The walrus is an endotherm.
And then I have my little lizard. He's an ectotherm.
That is all. All right, I'm going to leave circulatory for next time, I think. Yeah, we've got a couple more. Yeah. Okay. We've got a few more examples. We'll do circulatory adaptions next time.